Okay, so today I want to talk about our main idea for inference, which is likelihood. Hopefully most of you have at least heard of this idea before, but it's worth going over it. And so the idea is that a lot of the probability distributions that we're interested in are expressed in terms of a parameter. Right, so trivially, we have this Bernoulli, the chance that I hit or miss the target. Y is Bernoulli P. P is the parameter. It's also a lot of other things, also the expectation in this case. It's a little bit confusing. But in general, the parameter is won't have a direct mapping to the probabilities. It's just something that we can change and from which we can conclude what the probability distributions are. So here, okay, we have two outcomes, 0 and 1, and the probability of those outcomes is 1 minus p and p. That's just the definition of our distribution. Right? So slightly less trivially, if we let x be binomial, say 2p, meaning I've thrown two darts at the board and seeing whether or not I hit the target. Then we have three outcomes. X is 0, x is 1, or x is 2. And they have probability. Okay, well, how can I get x equals 0? I have to miss both times, so that's 1 minus p squared. And to hit twice, I have to hit twice, and that means that it's p squared. And then when x equals 1, either I can hit and then miss, or I can miss and then hit. Right. So there are a couple of things happening here. So when we have implicitly, so one of the things that's happening is binomial distribution is the same thing as n tries of a Bernoulli. Independent, identically distributed tries. When I have that situation, and I'm just interested in the count, like the number of successes, there's going to be a bunch of stuff in the middle which has binomial coefficients, right? Which is just, here the coefficient is 2, but later it's going to be 3, 1, 3, 3, 1, like Pascal triangle. So there's a extent to which we don't care about the order here, and these probabilities that all have the same count will all be the same, but they'll be formed differently, right? Okay, so if I add these up, this plus this plus this, that's equal to 1, right? Okay, so the probability distribution function, or probability mass function, is, well, it's just a function, f, and it has two inputs. Now we usually think of it as having one input, which is the outcome. But really it has two inputs because it's a function of both whether x was 0, 1, or 2, and what p was. So it really has two inputs, x. Sometimes people write a semicolon or a bar there, and theta. So I'll usually write a semicolon to distinguish it from conditional statements. Okay, so it's a function of the variables of the outcome. So here x is, in this example, would be 2, right? And the parameter okay, so and now if I have more than one probability distribution around, I need to keep track of which f I'm talking about. So I'm going to write f Bernoulli. So f Bernoulli, or Bernoulli 0 p is just 1 minus p. And f Bernoulli 1 p, so there's the two inputs, is equal to p. If I want to think about the binomial one, it's going to be different. So f binomial 0 p, where n equals 2. So I have to specify that, the number of outcomes. And there were two successes. That's going to be f Bernoulli 0p times f Bernoulli 0p. Right? That's just another way of saying this. It's like a sort of a fancier way of saying, or a more complicated way of saying what we said here. And I could keep going. F binomial with n equal to 2 of 1p is f Bernoulli 0 f Bernoulli 1 plus f Bernoulli 1 p times f Bernoulli 0p. Right? Not saying much here. So either first a 1 and then a 0, or first a 0 and then a 1, which is equal to some coefficient times just whatever this was not caring about the order. Okay, so this is a function of two parameters. When I'm thinking about it as a probability distribution function or probability mass function, I'm usually fixing the parameter and letting the data vary, right? And I draw a graph, you know, this approximates normal when probability is equal to 1/2 or close to 1/2 and n goes to infinity, right? That's the kind of graph we draw for the binomial. It's a chunky version of this normal. But, and if I do the other thing, which is I think of the outcome itself as fixed. So if I fix the outcome, that's a constant, and I let the parameter vary, I get another perfectly good function. Right? It has a different meaning. And that is called, so I have f of two parameters. If x varies and theta is fixed, we usually call this a probability distribution function or probability mass function. If x is fixed, the data is fixed, the outcome, and theta varies, we call this a likelihood. So I put a star here, and the star just refers to, well, since we're fixing the data, it doesn't really matter what row we're in. We don't have to keep, all we care about usually is maximizing it, like changing theta and maximizing and minimizing this function. And so these coefficients that show up in the middle, we don't care about them. So when I say a likelihood function, I usually mean this part of this, not ignoring the constant, because the constant doesn't make a difference for maximization. Okay. So we write something like the likelihood of this now fixed data x, not variable, and variable parameter theta is f of, the first outcome in the data set and the parameter times f of the second outcome in the data set and the parameter, and so on up to the last outcome in the data set and the parameter. And I've not worried about the fact that there's more than one way to get, say, one success in two trials. Okay? So that's a likelihood function. Now, for various reasons, multiplying, these are all probabilities and they're small numbers, and multiplying small numbers is usually a bad idea on a computer. And it's also hard to compute things by hand. And so for those reasons and other reasons, we usually work not with the likelihood function, but with the log likelihood function, which is the logarithm of the likelihood. And then this multiplication becomes a sum of the log of these numbers. Right? And usually this is written L, little l, of x theta log likelihood. Right? So if I'm interested in minimizing or maximizing this function as a function of theta, it doesn't matter if I remove the constant, and it doesn't matter if I take the log.
Well, if you talk about likelihood, so you say x fixed, but you have xi, xj, and
right, so I'm thinking of, so this is like a data set. X is a vector, x1, xn. So you should think about this as like I threw n darts, and this is the total outcome, right, of the sequence of throws. And this is what happens in each individual independent thing. Okay. So this is an important point. So it's a little confusing. This concept of likelihood makes sense both for talking about one single observation, one single throw of the dart, and a whole sequence of observations if they're independent, right? And it makes just as much sense. Another way of saying that is, you know, an entire data set is one observation, which is just a big observation, and a single point or a single outcome is just a very small data set. So likelihood makes just as much sense in either case. The distinction is really just that when we have an assumption about independence, like that n equals the two throws of the dart are independent, then the likelihood function or the probability distribution function has a special form, which is that it factors into the product of simpler functions. But that's the only thing that's going on. I mean, otherwise, this is just another probability distribution function, just as good as any other. This is a probability distribution function. Okay, so the idea is that this log likelihood function, we're going to want to maximize L of x theta. So we're changing theta, right? I'll say a little bit more in a second why that might make sense to do. But in order to solve this problem, it would sure be nice if this log likelihood function has a nice form, right? If it looks like this, we're in trouble. If it looks like this, hey, things are nice, right? Okay, so the theory tells us that for sufficiently nice statistical models, and I'll say in a little bit what that means. So nice basically means that they're identifiable, meaning I pick a parameter, or if I pick a probability distribution function, there's only one parameter that gives me that. They're sort of non-singular, and something called the Fisher information matrix is invertible. So when certain sort of technical conditions hold, we can say that as the number of observations, and I have IID observations, as the number of observations increases, this function, this log likelihood function, looks more and more like a quadratic function, like a parabola pointing down. And it's this asymptotically quadraticness that makes the normal approximation work. Okay, and we'll see different ways of understanding that. And I have to either you'll either be glad or disappointed to hear that in this class we won't be like proving these things. I'm going to try to give you intuition for you and point you to where you can read about it in a class like Stat 553, which I taught last year. You learn how to prove that these things happen. This function approaches are quadratic, and the maximum likelihood estimators are approximately normal, and so on. But you're going to have to take my word for it for the most part in this class. Okay, so why do we do this? So the idea that we should maximize likelihood is not really a mathematical idea, it's kind of a philosophical idea, right? So we see a data set, and we have to make a decision about how to model it or how to approximate it, right? So an a decision is this idea, is to estimate theta, choose the theta making the data most likely. Okay, so that's just a rephrasing of this, right? It says fixing the data, choose the theta that makes this probability highest. And that makes sense, but there's no sort of deep reason why that has to be true. And I want to emphasize that it's only one way to decide what theta should be. Okay. Can anybody think of a situation in which that's a bad idea? Well, suppose I did a Bernoulli trial or a binomial. So say I had a binomial distribution, right? I threw a chalk at the board a lot of times, and I hit this half the time and I missed half the time. What would your guess be that the parameter of how likely I am to hit it be? Yeah, 0.5, right? And that turns out that that is the maximum likelihood estimate. So what if I hit it a third of the time? The guess would be a third, and that would be a good guess, right? What if I just throw it once and I miss? Your maximum likelihood estimate is probably going to be 0, right? But that's kind of not a very good guess. Right? So when the data is small, when the data set is small, or even small with respect to the number of possible outcomes, this is going to give you a bad answer, right? You need, in those situations, you need to have some kind of regularizing factor. Or if you're Bayesian, you'd say you needed a prior. You had some kind of assumption about the range of possible, you have prior probability distribution over how good you think I might be, right? And you adjust that assumption after you see the data. Now, if we have enough data, that initial assumption gets washed out. And sort of frequentist statistics sort of takes the point of view that we can more or less always assume that that initial assumption gets washed out. We don't have to worry about this kind of error as long as we have enough data. Okay? And that's, you can formalize that and say how much data do you need, and we'll talk a little bit about sort of rules of thumb of how much data you need to be comfortable in that situation. But I want to make sure that you understand that these are, it's just an approach, and it can certainly go wrong. Okay, so faced with one of these functions, how do we maximize it? Take the derivative, exactly. So that's the usual way of doing it. Take the derivative. And more or less the only way to do it. Another way of saying that is we're using the, we're taking the derivative of the likelihood function with respect to theta. We're setting that equal to 0. This is called a first order condition. And if everything is nice and our function looks like this and not like that, that's going to tell us, right, that there's only one solution to this equation, and it's right here. We have the answer. Now sometimes we'll be in this situation where there's multiple local maxima, local minima, maybe there's inflection points and things like that. So if we don't have a nice log likelihood or a nice likelihood function, this may not give us enough information to decide where the maximum is. But it's the approach that we'll use most of the time, and it's the approach that's sort of implicitly used in the software a lot of the time. Okay, so two things can happen with this optimization problem. When we're lucky, for simple models like the Bernoulli model, or the binomial, or some of the other things that we'll discuss, like a Poisson, the first order conditions are solvable. You solve it, you can write down a closed form solution for the maximum for the, let's say, theta hat, which is the arg maybe I have a star there too. Arg max of Lx theta. We're changing theta. Right? So if we're lucky, there's just a simple closed form solution. You already derived one of those solutions, which is for the binomial, it's just the number of successes divided by the number of trials. Right? So that's one example of a closed form solution for a maximum likelihood estimator. And you can look in the notes, or maybe we'll talk about, you can quickly derive that by writing down the likelihood, but taking its log, taking its derivative, and then you'll get this number, or this relationship. But for a lot of the models that we'll use, there will be no closed form solution. And so we'll use the software. So there's optimization, computer optimization routines that run in R and SAS and other packages that try to solve this problem. Now, the way most computer optimization routines work is kind of just a more sophisticated strategy of taking derivatives. It might take second derivatives and so on. And so what it's going to do a lot of times is hill climbing. So it'll say, okay, we start here with this. We start with some initial guess. And we look at the derivative, and we move, and we move, and we move, and we move until we can't get any better. or the derivatives are 0, or it looks 0, and then we stop. The problem with that is if I start over here, it's going to do this, it's going to happily converge. It'll run and it'll spit out, here's your answer, but it's not the true global maximum. Okay, so, well, it's good. So I'd say one of the most common mistakes because of that in using statistics is actually when you have a situation where you don't have a guarantee that you have a unique maximum for your likelihood function. You plug it into the software, it spits something out, and you believe it. Okay, because I want to warn you that this can happen, and you should either be sure that you have only one optimum, or you can try by starting in different places, and there's formal ways where you can count the number of local maxima. Okay. So just the art of being worried about your data. That's one of the things to worry about. And sometimes your software will spit out a result that makes no sense, and that might be what happened. Right? So another thing that can happen is this. There's like a boundary, right? And you start out here and it hit the boundary. So if that happens frequently when you have like lots of zeros or something. So you might try to compute a maximum likelihood estimate, and you get something that seems really degenerate, and that's probably what happened. And just restart somehow, forcing it to be in the middle.
What is the ARG in front of max?
Oh, just arg, like theta hat is equal to the argument which maximizes this function. Okay, so this optimum theta star or theta hat arg max likelihood x theta is called maximum likelihood estimate. And again, we're not really going to derive such things except in the most simple cases. But you can take another class if you want to learn how to do that. I want to make another important distinction. So this is MLE, and MLE can kind of stand for two things, maximum likelihood estimate or maximum likelihood estimator. So let me make this distinction. If I fix the data, as we've been doing conceptually, then this number, the maximum likelihood estimate, is just a number. Right? It was determined when we fixed the data. Okay? Now what about if we let both the data and this parameter vary? Suppose that we treat x, the data, is a random variable. And we say theta star is the thing which maximizes the log likelihood of this random variable and theta. So what is theta star now? It's not a number anymore. You could describe something about it with a curve. It's not really a curve either, right? So I've applied a function. It's a complicated function. It's a function that's not closed form in general, but I've just applied a function to a random variable. So what do I get? If I take the number of times I hit the board and the number of times you hit the board when you throw me the chalk, I add those together. I've applied a function to them. I get a random variable, right? So this is a random variable. You can think about it as a function of the data, which is itself a random variable. And as Matt says, there's a curve going on here. What's that curve? Well, okay, so suppose this was the true parameter. Right. There's some true number. I hit the target on the board exactly a third of the time that I throw it. That's my skill level. I throw it 10 times, and I take the average. Okay, it's not even possible that I'll get exactly a third. I'll get 3/10 or 4/10 if I'm lucky. What instead I get is a distribution, right? And maybe it looks like that, right, if we're lucky. So this is a probability distribution function of the random variable beta star. If you think about it that way, the maximum likelihood estimators that my model spits out is a random variable which has a distribution, and we'd like that distribution to be centered around the truth and to have variance that's not too big, and we'd sure like it to be approximately normal. Okay? And when the model is nice and clean and satisfies technical conditions, this curve, this probability distribution of the maximum likelihood estimator around the true parameter will look exactly like that. It'll have the right expectation, that's what we call unbiased, and it will be asymptotically normal. And that's what allows us to do these confidence intervals, right? So if I say, okay, give me a confidence interval for the true parameter, that's why I can use this 1.96 standard deviations. And I say, oh, give me one standard deviation on each side, or 2 standard deviations on each side of the estimate. So that's why that's kind of one way to think about how these normal distributions, normal approximations make sense. Okay. So it's a random interval. Things like confidence intervals are also functions of the data, and we should think of them as random variables, just complicated random variables. Okay, so you should be aware that this assumption too can be violated. Let me give me an example of when that assumption could be violated, this asymptotic normality around the Now what if I'm flipping a biased coin or I'm throwing chalk at the board? Okay, how about this is my target? Right? I throw it 100 times or something. I'm almost never going to hit it, right? And any kind of heuristic that says take a look at a standard deviation and add and subtract some number to it, right, it's going to end up with stuff that's less than 0 in the confidence interval. That's one way of thinking about how it fails. Another is that if I'm piling up all my mass really close to 0, there's no room to fit something that's approximately normal. Right? If my mean is really close to 0, there's just no room. So it's not going to look right. Maybe we'll formalize that a little bit more. But basically, so in the Bernoulli or binomial case, when your probability is close to 0, your probability is close to 1, the assumption breaks down. And a lot of the techniques that we'll learn that are sort of more sophisticated ways of constructing an MLE, more sophisticated ways of constructing hypothesis tests, are ways around that problem. Ways to make sure that we can use our asymptotic normality and we don't do something like run over the edge of the plausible interval. Okay. Okay, so the point is to be somewhat suspicious. Now let's take a little video break here, and I'll pull up a couple of pictures. And I'll get back to talking to you. So any questions while I turn on the computer here? Is this all stuff that's fairly familiar to you, or not that familiar, or anybody? So maybe it depends on how recently was the last statistics class you took or something. This one's a little bit rough still, this likelihood one, but I'll try to make it a little bit more instructive as we go on. It's good, by the way, if you have as a way to get familiar with your software package and also to get a sense for how much data is enough data, if you experiment a little bit with these things and see how much, how many observations do you need before something looks approximately normal? How many observations do you need for the likelihood function to start getting clean? All right, so here's an example. I have a binomial distribution, 5 outcomes with chance 0.3 of success. I can sample from that with this command rbinom, and dbinom is the distribution. Here's 1,000 draws from that distribution. Okay. When I did it at home, it didn't make a long list. It printed it all in a grid, so it only took up a little bit of space. Okay. So we take the table like that. We can summarize it in terms of the proportions with this bar. So table tabulates this and just counts how many of each possible outcomes there are, and then bar plot says to plot it. So here's what the outcome looks like. All right, it looks sort of very approximately normal. If the numbers were much bigger, it would look better. So that's the counts. I can divide by the sum to get the proportions. So that's the probabilities. Oh, look at that. And now we can plot the likelihood. Wow, that's terrible. Internet Explorer. Is this a really old version of Internet Explorer or something? It worked yesterday, though, right? Or not yesterday, it worked on Tuesday. Oh, okay. Anyway, so this is just the label for up here. We're saying what situation we have. We have 2 successes, or 2 failures, 1 minus p, and 3 successes. And then we can plot the likelihood function. So I vary my parameter p, and I have a likelihood of p given the fixed data, and this is what that likelihood function looks like. This is a nice likelihood function. It has a very clear peak, and that peak coincides with, well, in this case, 1 minus p. I can do it for other values, and for other values, like when I have fewer successes, say I only have the event 1 minus that happens with probability 1 minus p happens 4 times, and the probability with chance p only happens once. Okay, so then it's still approaching that shape. This is the log likelihood. It's approaching like a quadratic shape, but it doesn't look very much like it yet. If it's closer to the middle, like I have 2 successes and 3 failures, then it's starting to get a nice thing that looks sort of quadratic and has a clear peak. If I do it, many, many times, then it's a very, very clean function. And here's just an example of binomial approaching normal. So here there's 50 outcomes, and I do 100,000 trials. You can see it starts to get very nice. Anyway, I recommend just like playing with those things a little bit, just to get a sense for how much is a lot of data. When do we get close to infinity? Okay. So let's continue. Okay, so for the I'm sort of giving you the overview now. I'm gonna actually do some calculations. So okay, so for the Bernoulli, I have some, let's say, or Bernoulli binomial, let's say. I have n trials, and they're independent. And I can write down a likelihood function which is just the product of the PDFs at each of the trials. Right? So I have some probability of success, and I have 1 minus that as the probability of failure that otherwise happens. And I can take the log of this function, and then this becomes a sum, and I can take the derivative with respect to p, and I set that equal to 0, and I solve that equation, I get what you'd expect, that it's just the sample mean. Okay, so for binomial, what does that look like? Likelihood if I include all my factors counting the way things can happen. So this is where the action is, and then this is the coefficient that counts how many times I can get this many successes and this many failures. We could take the log likelihood function, which is some constant that corresponds to that we don't care about, plus x log p plus n minus x log 1 minus p. And if you take the derivative, you'll get, again, that it's the sample mean. All right, so one of the most frustrating things in learning about maximum likelihood is oftentimes you set up some big complicated thing and you end up proving, it's the sample mean. It's the sample mean again, right? And you're like, why did we do all this? But, okay, the reason that people often do that is because, and you'll see that if you read about it somewhere, is because the times when it's the sample mean is one of the times when it's easy to calculate, right? We can actually work it out. Lots of times the maximum likelihood estimate will be either a really nasty formula or, like we said, there'll be no formula for it. And of course we couldn't explain that on the chalkboard. Let's look at another case of sample mean, which is Poisson. All right, I'm going to bring this up. This shows up in your homework. Okay, so we got a random variable which is distributed with some with a parameter lambda. And the mass function or distribution function is lambda to the x e to the minus lambda over x factorial. So x is just a number, and lambda is a positive number. Because lambda is a positive, non-negative integer. Lambda is a positive number, and the expectation of this is equal to lambda, and the variance is equal to lambda. Okay, so that tells you right away that you have a way of testing whether something is a Poisson or not. You should be able to compute its expectation and variance, and they should be the same. when the variance is larger, that means something else is happening. So the Poisson you should think about as you have a constant, something's happening over time or space. You have a constant hazard rate lambda that an event will arrive in a certain interval, and there's absolutely no correlation between intervals, right? The other way to think about it is as a limiting case at the binomial. So if you say we have x, which is binomial, with some n p, and we let n go to infinity, and we let p go to 0, and np goes to a constant. Right? So what we should think about is I have some interval of time or space, and I divide it up, and I divide it up, and I keep dividing it into smaller and smaller pieces, and at each time the chance of success goes down proportionally. Right? Okay. Then we can say that for large n, large n meaning n big enough that these intervals always have only 0 or 1 in them, right? So like the intervals are small enough that there's never two things that happen in one interval. That's the point of doing this. When we do that, then n factorial x factorial n minus x factorial p to the x 1 minus p to the n minus x is approximately lambda to the x e to the minus lambda over x factorial. So that's the sense in which for large n, when these things are satisfied, the binomial and the Poisson start to look the same. Okay, so that's the definition of the PDF, and so the likelihood function, if we observe, so suppose we observe a bunch of intervals, right? So we take we believe that this thing is the process that's generating the data is totally smooth, there's no autocorrelation, there's no variation in hazard rate over time. And we observe a bunch of chunks. So we observe x1 up to xn. Each of these things is Poisson. So each one of these is a count, number of events that happened in the time period. All the time periods are the same. We have a likelihood function, which is just, well, because of the independence assumption, like every other likelihood function with an independence assumption, I just take the product of all of the probability distribution functions here. So that's lambda to the sum, I equals 1 to n xi e to the minus lambda or e to the minus n lambda over x1 factorial, x2 factorial, up to xn factorial. Okay, and then we could take the log likelihood function. So log L of x lambda is the sum I equals 1 to n xi log lambda minus n lambda. And ignoring the constant terms in our maximization, you get that the maximum, taking the derivative, shockingly, is so we're trying to estimate the parameter lambda, and it's the sample mean. So number of observations divided by number of periods that we looked at. Okay, so now let's look at forming confidence intervals for these things. There's one confidence interval problem in your homework. So assuming that the technical conditions we need for our asymptotic normality to hold, we're saying that our, whatever it is, our theta hat as a random variable, we convince ourselves that as a function of the data, when it's a function of the data, it's a random variable, is approximately normal with mean, the true mean, and some variance. And of course, we don't know the true mean and we don't know the true variance, so we have to really estimate these things. And we can use that information to create these sort of simple interval estimates. Right? We believe it's normally distributed, and we can just chop it up to find a confidence interval. So the simple confidence interval or walled confidence interval that you may have probably seen before is you just take 1.96 and you multiply that by the square root of the estimate of the variance. And this is called a walled. So it turns out that this is a tragedy of statistics, right? So this is the most commonly used confidence interval, and in a tremendous amount of the research that you look at, it's not statistics research, but it's just research on some topic. They'll compute this variance, and they'll use that as the confidence interval. And we'll learn a couple of different ways of constructing the confidence interval, and it'll turn out this is the worst one. Okay? There's a couple of other ways of doing it that don't suffer, where essentially in the other methods, this approximation is better. The speed with which it reaches an approximately normal random variable is quicker, and this one is, while easy to do and easy to think about, is usually not the one you want to use. It's interesting because we can construct such a thing for our binomials. Let's see if I do this one. I'll leave that to a second. To a little bit later, before we do it explicitly for our examples. So there are a couple of other, so this has this quantity here, which is the variance, not of the random variable, but the variance of the probability of the maximum likelihood estimator as a random variable. So it's the spread of that curve that lies over the true value. And a lot of the technology is in both estimating theta hat, but also in estimating that quantity. That's a totally unknown quantity that you can't tell from your data. Right? How much does your estimate of theta hat spread out? So there are a couple of different ways of thinking about that, and they're related to this idea of information. So I said earlier there was something called a Fisher information matrix. And let's talk about how that's related. So there's something called observed information, which is just minus the second derivative of the log likelihood at your estimate, your maximum likelihood estimate. I'm using the other order. So this is called the observed information, and there's an approximation for this number, this standard error, which is just 1 over this observed information. 1 over the square root of minus L prime prime x theta hat is an estimate of the square root of the variance of your maximum likelihood estimator. So that gives you another interval. Instead of, you just replace this square root here with this quantity, and you get theta hat plus minus 1.96 1 over square root of minus L prime prime of x theta hat. And there's another kind of information called expected information. I of theta equals minus expectation of L prime prime of theta hat x. So it's always, or it's frequently the case that you want to move from things which depend explicitly on the data to things that depend less on the data because you're integrating over an expectation that depends on some other parameter, theta. And it helps your theory because you don't have to look at anything. This is called expected information. Fisher information. And when I have a multivariate version of this, this becomes a Fisher information matrix because I take a second derivative. So these quantities, these second derivatives of the likelihood, why does a second derivative of the likelihood function show up here? What does it have to do with what we talked about earlier? Anybody have a guess about that? Like the pictures that I drew on the, or that we drew on the computer. Where is this second derivative coming from? Why is that interesting?
You need a second derivative to determine its actual maximum.
That's true. If the second derivative is in the wrong direction, we're really, it's hopeless. But what does the information of that second derivative tell you?
The information of the log.
Yeah, the second derivative of the log likelihood function.
None of that.
So I draw like a curve. What does the second derivative of that curve tell you?
The rate at which the derivative changes. So based on how drastic the second derivative is, it talks about like how flat or how steep.
Exactly, right? So we want to be in a situation more like this than like that, right? So the tighter this curve is, the stronger that second derivative is, the more information we have about where the maximum likelihood is. And as this gets flatter, you can think about it as it's easier for this, our guess as to what theta to be to move around, right? It's harder for us to tell where the maximum is. So that's kind of what's going on here. That's why this is related, like this quantity is related to the variance. And if we were in multivariate case, this is going to become like the second derivative of like a cone surface. And it's not a very good picture, but you get the idea. And that's the Fisher information matrix. Okay, so let me go to a specific. Oh, sorry, I should say that you can also use this to construct your confidence interval, which would be theta hat plus minus 1.96 1 over the square root of I of theta hat. So let's just go through an explicit example of constructing this for, or not, a little bit more detail of constructing this for a Bernoulli. X Bernoulli, our likelihood is x log p plus 1 minus x log 1 minus p. L prime of p is x minus p over p 1 minus p. L prime prime is minus x minus p squared over p squared 1 minus p. And expectation of x minus p squared is equal to the variance of x p 1 minus p. And so this Fisher information, I of p, which is minus the expectation of the second derivative of the log likelihood function, is equal to something very simple, which is just 1 over p 1 minus p. Okay, so we knew this is the theoretical variance anyway, so it's, in this case, kind of there were different ways of computing it become the same thing. If we have, of course, one observation is kind of a bad way to decide what the probability is. So if we look at the binomial version, the log likelihood has this x added to it, which is now a number between 0 and n. And we have a first derivative and a second derivative. And we compute the Fisher information. To the n over p 1 minus p squared, just p. And so a 95% confidence interval has a nice closed form. A walled one based on the Fisher information is 1 plus minus 1.96 p hat 1 minus p hat over n. Okay, so let me stop for a second and say, okay, so that was just some calculations. You can look at the notes or work through the calculations yourself. The point was that in some cases, like the simple case, it's easy to construct a closed form for the 95% confidence interval. And now I just want to make some comments about that. So, okay, p hat is our obvious maximum likelihood estimate for the binomial distribution. Number of times that I hit the target when I throw the chalk at the board, number of times that I get a success when I flip a coin that's biased. And my maximum likelihood estimate of that is just number of successes divided by number of trials. We've already convinced ourselves that when n is very small, it's not a very good estimate. When n is big, it's a pretty good estimate. And the new piece of information is using this idea that I just quickly went through, we can get an estimate of the variance of this estimate, right, based on Fisher information, expected information. And using that estimate, we can construct a confidence interval. This is a walled type confidence interval. It lives in this probability space, and it just adds and subtracts a number to it. Okay, so if p is very close to 0, p hat is very close to 0, very close to 1, this is going to include numbers which are not between 0 and 1. Okay, so that's one clue that it's not so good. It's an absolutely, in my opinion, mind-blowing fact that here in 2016, 115 years after people started thinking about this stuff, we still don't know how to construct a correct 95% confidence interval for the binomial distribution. Okay? What I mean by that is if you go to your computer and you pick a p, a true p, right? You pick a p true, and you simulate it, right? So you draw a billion, you flip a billion coins, 10 billion coins, you flip a trillion coins, or you flip 100 coins. A better thing would be you flip 1,000 coins, you construct a confidence interval. You flip 1,000 coins, you construct a confidence interval. You do that, right? A million times. If you've constructed a correct 95% confidence interval, every time you make that confidence interval calculation, either the true thing will be in there or not. If it's correct, it will be in there 95% of the time. Right? it will be in there. If you really did that using this, it's not very close to 95%. It'll be higher or lower, depending on the choice of P. True. There are improvements. So people, even in the last 5 years, continue to write papers about, okay, here's a slightly better way to construct a confidence interval using some different technique for which that experiment I just described will get closer to 95%. The truth is that nobody knows. It's an open question how to construct a correct 95% confidence interval for flips of a coin. And that's, I don't know, almost embarrassing. We've been working on this too long for such a simple thing. But, okay, I wanted to tell you that because it gives you a sense of, don't just take you're going to be using canned procedures in R and SAS and everything else. But keep in mind that all of these things are moving targets. And in many cases, all we have is an approximation that we even know is not the right approximation. Okay, so one other observation I want to make about this and this notion of information. So Fisher information is additive among independent trials. You can think about the Fisher information of an individual trial, like the Bernoulli thing, as being like, how much more information do I get about the true distribution or the location of my theta with each time I flip the coin. And each time I flip the coin, I get a little bit more information, and the thing gets steeper and steeper and steeper. But what it's sort of measuring is that quantity. So another way of saying that is, if you look at these numbers, Fisher information for binomial NP is just n times Fisher information for one Bernoulli. And that's true whenever our IID draws. Okay? It'll be true that their Fisher information is add. So in this case, there was this other thing that I mentioned called observed information. In general, the confidence interval or the hypothesis test that observed information will give you is not the same as the one that you'll get from expected information. But in some cases, they're equal. So in this binomial Bernoulli case, it happens to be that they're equal. So if you did observed information, which was the second derivative evaluated at the MLE, and that's going to be the same interval that we get. That's going to lead to the same interval we get when we go 1 over square root of that that we got from the observed information or the expected information. Essentially, the reason for that is there's degeneracy sort of comes from the fact that the maximum likelihood estimator is very simple. If it wasn't a simple estimator, these will generally be different. So I have a paper actually about this. I'll post it on Angel about this issue that this. Not my paper, but someone else's paper talking about the issue that we don't know how to estimate what the bias of a coin is. So we'll talk about some fixes for this issue of going over the edges. Usually the best kind of fix for this is to do a transformation on the space. So, instead of okay, so we have this function which we're hitting these boundaries, and we can remove the boundaries by switching to a function like that or something. Right? I don't know, that's not a very good example. Sorry. We should switch to a function like that. Right. If we do some kind of a transformation of this space to remove the boundaries, that usually helps fix the situation. And so we'll talk about how to do that. A more ad hoc thing you can do is you can just add numbers. So suppose you've done this thing, you observed, we threw chalk at the board, we observe no successes. We can make a new estimate, which is just the number of successes plus 1/2 divided by the number of trials plus 1. Okay, so in a big contingency table, it's kind of like you take a bunch of things which are 0, you add a small number to them, then you add that same number to the total. That's a pretty brutally heuristic approach, but it turns out that it works pretty well, because oftentimes we just need to get away from the boundary, and as soon as we do that, the algorithms and the statistics work okay. There are much more sophisticated ways of making that correction, like by using Bayesian technique, or by using this kind of transformation. But in many cases, you might find that this is perfectly okay, and just adding something to each cell gives you a reasonable answer. Okay, I think I'll stop there today, and give you time to ask any other questions you might have, or logistical questions.
If I give that to Mark, since I haven't been put in, I think on Angel yet.
Oh,
I still have to wait for this to go through.
just send me an email and remind me. I can add anyone to Angel. Just I have to
Okay.
add another person in here to Angel too.
Okay.
Yeah, just send me an email.